Okay, we're looking at logic states, and we're completing section 15.1. Digital devices operate on binary values, so there are only two allowable digital states. Each of these states is called a logic state. A variety of names are used to label these two states. And typically we're looking at zeros and ones. And a logical one often is indicated by true, high, yes, on. Logical zero as false, low, on, or no, or off. And in the context of digital circuits, these are terms that are commonly used to reflect either a 0 or a 1. Sometimes the logic state is indicated by the presence or absence of a voltage or differing polarities of the same voltage. By far the most common is by the presence or absence of a voltage. Typically a low is 0 and a high would be plus 5 volts. So there is a trend towards lower voltages. Sometimes in computer systems you'll see a low is 0 and sometimes a high can be as low as possibly 2.3 volts. So at any rate, the low is indicated by typically 0 and the high by a little higher voltage. Truth tables. Truth tables provide a way to describe the relationship between the inputs and outputs of a logic device. And so below here is depicted a truth table. And here we have a logic device. In this case, we have two inputs and we have an output. Now, since our outputs or inputs can only be zeros and ones, there is a limit to how many possible varieties of inputs we can have. So what a truth table does is it indicates all of the possible inputs that we could get from these two inputs. And so since this is binary and we have two inputs, we'll have 2 squared. This is the number of possibilities that we'll have for inputs. And so you see here we have 0, 1, 2, and 3. So those indicate our 4 possible inputs. And typically A is considered to be the least significant variable in a truth table, and so there we have A, and then again 4 possible inputs. If we'd added a third here, then we would have 2 to the third, where we'd have 8 possible input values. And then here in the Y, we see what is the resultant output. But again, this is a truth table, and it shows us all of the possible inputs and outputs for a given logic circuit. Timing diagrams. Timing diagrams also show relationships between input and output conditions in a logic circuit. And so here we have our logic circuit. Here we have 3 possible inputs and 2 possible outputs. And here we're showing, and this is typically what you would see in an oscilloscope, it's reflecting the highs and lows, and these are the inputs, and then these are the resulting outputs. We're not going to analyze this at this time, but this is typical of what you would see concerning inputs and outputs into a digital logic circuit. Boolean algebra and logic gates. Boolean algebra provides a means to describe and understand the behavior of logic circuits. Boolean algebra describes the relationship between input variables and output variables. Logic diagrams also provide a way of representing a logic circuit. It is critical to understand Boolean algebra and logic diagrams in today's electronic environment. Okay, logical operators. Boolean algebra will utilize logical operators. Only a few logical operators exist to describe logic relationships. These fundamental operators are not, and, or, and exclusive or. And so we're going to be looking at these operators on the next slides that follow, and we'll be looking at the Boolean expressions for these operators. The first one we're going to look at is the AND operator. AND. The Boolean expression for a 2-input AND gate is, and here it is, Y equals AB. And it is read as Y equals A and B. And you could look at that it is effectively A times B. As shown, the output Y is high only when A and B are high. And so this is the representation for AND. You have a flat here, flat surface, and then you have the two inputs coming in, and you have an output. And here is the associated truth table with two inputs. We're going to have four possible inputs, so there'd be 0, 0, 0, 1, 1, 0, and 1, and 1. And what you'll note is the only time that you'll have a high out of this is when both the inputs are high, then you will have a high out. Electrically, you could view this like this, that the only time that you'll have illumination of this lamp here represented by Y is when both switches are closed. So this is the AND gate. Okay, the next basic gate is the OR gate. The Boolean expression for a two-input OR gate is Y equals A plus B, and it is read Y equals A or B. As shown, the output Y is high if either or both A or B are high. And so the expression here is, and you have a curved front, and you have the A, this would be the two inputs, and this would be your output. Remember, the AND look kind of like this. This would just associate it from an OR. So again, here is our truth table, and recall that you're going to have a true, or you're going to have a high out if either A or B is high. So in this case, the only time you will not have an output is when both A and B are 0. And so the truth table looks like this. If I have one good input, then I will have a high out. And this would be the associated circuit. If either of these switches is closed, then I will have illumination in Y. And if both are closed, I'll still have illumination in Y. So there is an OR operator. Okay, the next one is the NOT operator. The logic expression and Boolean expression for a NOT operator is Y equals, and you see that line over the A means not A. And it is read Y equals not A. The line above A is called a vinculum and indicates the NOT complement function. The NOT operator is also referred to as notice here, an inverter. And this is the logic diagram. You have the amplifier symbol, and then the 0 here, which means this is the NOT operation. Here is the truth table. If A is 0, Y is 1. If A is 1, Y is 0. And if you recall from transistor theory, an inverter can be implemented with a transistor. And in this case, if we had a high coming in, the high would come in, it would turn on the transistor would saturate, and it would look like a closed switch. Typically you have about 0.1 volts between the emitter and the collector, and for this purpose that would be effectively 0. If we came in with, and so that would be the high in, and you'd get the low out. Now if we came in with a low, which is effectively is a 0, the emitter-based junction would not be turned on, the transistor would effectively be off, and the 5 volts here would be felt on the collector. So here you have the low in, but effectively you would have the 5 volts reflecting a high out. And this is the NOT operator. Next is the NAND operator. A NAND gate is very widely used logic function. It is a combination of notice, an AND gate and an inverter. So here you have the AND gate, and then the little 0 here is the inverter. The small circle at the output indicates, okay, the inversion operation. Now this will give us an output that is exactly the opposite. If we had our AND gate, it would be exactly the opposite of an AND gate, because whatever you get out of the AND gate, it is not. Okay? So in this case, if I have a 0 and a 0 coming in, it's going to be a 0 out, but now it's inverted, so it's a 1. A 0 and a 1 should give a 0 out, but since it's not, it's a 1. The only time that I'll get a 0 out is if I have a 1 and a 1, which would give us a 1 out of the and, but then it's not, so it becomes 0. And this would be one way to implement this. Again, we would have the, if we have a 1 and a 1, that would give us a voltage here, but it would be inverted, so that would give us a 0. Okay, next is the NOR operation. The NOR operation is another very common logic function. It is a combination of an OR operator and an inverter, NOT. So remember again, we had the OR function, and it would give an output if either A or B was high. And so, but now since it's knotted, then it's going to be just the opposite. So if either A or B is high, then we're going to get a 0. And this is just the opposite of the OR operation. And the only time that we'll get a high out here is if we have a 0 and a 0, then we will get a high. And a way of implementing that would be this circuit right here, where we will get a valid input if either A or B is high, but then it is going to be inverted. So that would reflect this truth table. Then we have the exclusive OR operator. The exclusive OR operation performs the logic function that Y will be true if either A or B, but not both are true. So this is what we call exclusively OR, meaning that you have to have one or the other, but not both. And so you'll see here the only time that you have a valid output, a 1, is when both A and B are different. So a 0 and 1 gives us an output, a 1 and a 0 gives us an output. But if it's a 1 and a 1 or a 0 and a 0, there is no output. And you see electrically you could implement this like this, where here we have a 0 and a 1 which illuminates the light, or a 0 and a 1 here which illuminates the light. But if these are switched for 0 and 0 or 1 and 1, then there will not be a complete circuit. Okay, this has introduced our basic logic gates. So we looked at exclusive OR, we looked at NOR, NAND, NOT, OR, and we mentioned Boolean algebra, and we will spend the next section, we're going to talk about Boolean algebra quite a bit more. We looked at the concept of timing diagrams and truth tables. And so this concludes section 15.1.